Hey there, in this video we are talking about the basic data types that exist in the C++ language. And this covers basically sections 2.6 to 2.12 in the Gaddis C++ book. Now, I'll say that previously we've seen a couple of the data type possibilities in C++, but in this video we'd like to kind of get a more comprehensive look about what all the possibilities are. Some people in the world call these the fundamental data types. Some people call these primitive data types. I myself might call them the atomic data types, but whatever you call it, they are the basic building blocks of storing data in C++. Okay, so let's start with the integer data types. And you are certainly aware already that the keyword in C++ for that is int. Here's some more details. So integers, of course, are the most basic data type in any programming language. Here's the thing, in C and C++, the size of the data types, and we'll be wanting to think about fairly clearly about how much space in the memory system any particular piece of data is taking up. So for ints, the size of the data types can vary by the system that you're running on in C or C++. The C++ languages try to work very closely with the exact hardware, with the exact machinery of the CPU. So if you are working on some kind of microprocessor on an embedded device versus a smartphone versus a desktop versus maybe a supercomputer, however big the storage locations in the CPU are, and those are called registers, they're going to be smaller or larger, and C++ will generally try to make the integer type the same size. So it will vary between possibly different computers. Now that's different from a language like Java that dictates that an int is exactly one particular size no matter what kind of computer you're working on. Now, for example, in our systems working on Dev C++, currently the int size is going to be 4 bytes. Now remember, there's 8 bits per byte. 4 times 8 would tell you that's really 32 bits if you want to think about it that way. And if you do a little bit of math, you'll find that what you can do is you can store integers from about -2 billion up to +2 billion in that space. There's a little bit of math. I might show you some other day about exactly how to determine that, but it's a fairly simple calculation, honestly. Now keep in mind, any particular data location on a computer is going to be finite and have limited size, and you always have to think about being careful about those limits. For example, the population of New York City, about 8 million people, you can store that number in an int perfectly fine. The number of people in the United States, about 300 million or so, you can store that number perfectly fine. The number of people in the whole world, well, that's about 8 billion. You cannot store that number in an int. So if you want to store a number that large, you have to go and use some other type of data. So be aware of that. Now, there's a couple of modifiers that you can add to an int declaration. You can ask for a long int. You can ask for a short int. And what you're doing there is you're requesting more or less space. As a result, you're going to be able to store, hopefully, a larger or a smaller number range. So for an example, in our current version of Dev C++, the short int is only 2 bytes. Right? That's half as long as a normal int. That would be 16 bits. And as a result, you can only store smaller numbers in there, from about -32,000 to about +32,000. And that would be fine for a lot of purposes, but it's a lot more limited than the standard int. You also have modifiers of signed and unsigned, which get used to specify whether negatives are allowed. So if you ask for a signed int, you're very clearly saying we need to track the plus or minus sign because we might actually use negatives here. Of course, that's what ints work like anyway, so you'll probably never have to ask for that. But on the other hand, if you ask for an unsigned int, you're saying we will definitely never store negatives here. Don't worry about storing that piece of information. Use the whole thing for the 0 and the positives. So whereas previously you could store numbers from about -2 to +2 billion, and that's about 4 billion numbers, for an unsigned int, you're going to be using the entire range from 0 to the positives, and therefore you can count up to about 4 billion. So keep that in mind. Next type. Okay, so floating point data types, right? And there is a type called float. There's a couple other subtypes of floating points, but they all kind of work the same way. So the idea of the floating point data types is to represent real numbers, like any place on a real number line, or in other words, things that can be expressed with decimal point notation. That's the basic idea. Now, the specifics of that in C++, there are at least 3 subtypes for floating points. There is the float, which takes up 4 bytes of space. Now, technically, I think the technical name for that is the single precision floating point type. Single precision floating point type, and that takes up 4 bytes. Notice that's actually the same as an int. Then, you might actually be more familiar with this. There's the double precision floating point data type, or double in C++, and surprise, surprise, it takes up twice as much space. It takes up 8 bytes. That's why it's called the double. It takes up twice as many bytes as the single precision float. And then there's also a long double type, which on our current systems actually takes up 16 bytes of space. That can actually vary on different systems. There's a somewhat larger story behind the scenes that I'm not going to get into here, but on our current systems, that actually will take up 16 bytes of space. There's actually an international committee called the IEEE, which has set down standards for how floating point data types are supposed to work. There's a couple different options, and there's a somewhat deeper interaction between how your language, C++, works versus how your hardware works versus what the international standard is supposed to be. So that can get a much deeper conversation, but for our systems, this is how much space they take. Now, aside from that, the main thing that I think you should know about floating point data types, at least to begin with, is basically they get stored like scientific notation. Okay? If you know enough about scientific notation, that internally is exactly how floating point variables get stored. So scientific notation, something like 5 times 10 to the power 8, right? The 5 is called the coefficient. You have this times 10 part, and then there's an exponent like that 8 there, and that's how you store a scientific notation number. And that is exactly what floating point data types do. For example, the float type, remember 4 bytes, that's 32 bits, actually uses 24 bits for the coefficient and 8 bits for the exponent, right? And there's also the times 10 part we know about already, so we don't bother to save that. So 24 bits for the coefficient and 8 bits for the exponent. Now, those are bits, right? If you take those binary bits and you convert that information to decimal, you'll see that one of these single precision floats has about 8 coefficient digits. When you look at it in decimal, 8 coefficient digits of accuracy. And as far as the exponent goes, they can hold numbers from about 10 to the power negative 38, that's pretty small, right, up to 10 to the power positive 38 as far as the exponent magnitude goes. So you kind of want to be aware of that. Now, the other thing about floating points is, of course, again, they are limited, right? They have a limited space for the coefficient. So your calculations always have to be rounded off in order to fit in that space. Quick example. So let's say I try to store the number 1/3 in a single precision float. So you probably know that 1/3 as a decimal is 0.33333 repeating forever. But the single precision float doesn't have an infinite number of coefficient digits. It only has 8 if you look at it in decimal form. So at some point, the repeating 3's get cut off, right? And you save something that's somewhat shorter. Now that's going to be pretty close to the number 1/3, but it's not going to be precisely the number 1/3. It's going to be a little bit different. And you have to be kind of aware of that your calculations are always being approximated when you're using floating point data types. Now, if you're doing scientific measurements, you should realize that any measurement has a level of precision, or what I kind of want to call a margin of error to it. So you have to have those conversations in a science class about the precision of your measurement. So it shouldn't be too surprising that the same kind of thought process has to go into using the floating point data type in C++, or really any computer, that you would be using to store those measurements. Not too surprising. Of course, the additional thing is that the information is actually being stored in binary bits. So if you convert from the binary bits to decimal, at the end of the precision range, there'll probably be something even more surprising that you probably wouldn't guess at the end of it. But you can only depend on the precision of the first 8 decimal digits. And then the same story for the other types that have somewhat more precision. If you want complete precision in computer-based math, you've got to use an integer. If you do want to use a floating point data type, you have to deal with and remember about this precision accuracy issue. Okay, next type. So there's, of course, the character data type, and the keyword in C++ is char for characters. So characters are alphabetic type symbols, probably something you'd see on a keyboard or something like that. For example, letters of the alphabet, digits that you see in a number, punctuation, spaces, tabs, all kinds of stuff like that. Internally, you should be aware that these things get encoded as 1-byte integers. Everything on a computer is really a number, essentially. I say that from the software perspective. So the question is, how do those symbols get stored as numbers in 1 byte each? And the answer to that is that there's a system called ASCII, which stands for the American Standard Code for Information Interchange. And when these kinds of computers were first developed in the United States, this was the encoding system that said, these letters of the alphabet, we're going to store them as these numbers in the bytes of our computer system. In the Gaddis C++ book, there is a complete list of the ASCII table of what numbers get used to store what characters, and that's in either Appendix A or Appendix B, depending on what edition it is. And it might be interesting for you to look that up and be kind of aware of exactly what numbers get stored as what characters. Most of the time, our C++ compiler will take care of that issue for us, and we won't actually have to think about that as programmers. But once in a while, when we dig into the details, we might actually want to be aware of that. So sometimes we might actually turn to that appendix to be aware of exactly how our characters are being stored as numbers. And keep in mind this. So these are numbers, right? So alternatively, you could use the char type to store relatively small numbers. In fact, once in a while, I do that. For example, 1 byte, right? A character is 1 byte. That's 8 bits. So every bit that you add to a data type gives you ×2 as many possibilities for things you could store there. A bit has 2 possibilities, so as a basic probability counting thing, every bit gives you ×2 the possibilities. So with 8 bits, I would have 2 times 2 times 2 times 2, 8 times, or in other words, 2 to the 8th power number of possible things I could store there. Well, 2 to the 8th is actually 256. And what happens is we use half of those numbers for the negatives, and we use half of those numbers for the non-negatives, for the 0 through the positives. And when you do that, you see that the possible range of numbers that you could store there goes from negative 128, 128 is half of 256, up to positive 127. For what it's worth, that's the math that you use to convert from the number of bits to the possible range of numbers you can store there. You could go back 2 slides actually, and you could redo that for the 32-bit int, and you'd see that the numbers work out for that. You can also attach the modifiers signed and unsigned to a char if you are using it for a number like this, and so once in a while I might do that. The reason I would want to do that in class is just to make for a very small example. If I want to look at all the bits of a particular data type, it would certainly be easier to look at a data type that just has 8 bits rather than 32 bits for the whole int. So that's why I sometimes do that in class. And here's the last basic data type. It's called the Boolean data type, or bool for the keyword. It's actually named after a mathematician named George Boole, who studied these kinds of things in the past. And the Boolean is a type, very, very simple. It only has 2 possible values. It's either true or false. You would actually see that on the screen if you printed it out. Now again, everything's a number. So internally, to store false, you are actually storing the number 0. When you're storing true, on C++, that could actually be any non-zero value would get counted as true. It's probably going to get stored as the number 1. And in Dev C++, this uses 1 byte, the same as a char actually. I suppose if you're really thinking about this deeply, you might say, hey, wait a minute, don't I only need 1 bit for that? I should really just need 1 bit, 0 or 1, to indicate the false or the true. And there are some more advanced ways of like packing in more Booleans into smaller space, but just for starters, the regular Boolean takes up 1 byte, and that's perfectly fine. Okay, so let's talk about this. So we saw 4 basic families of data here, right? The integers, the floating points, the characters, and the Booleans. So you can declare variables of any of those types. We saw that in the last video on declaring and using data in general. But you can also type these values directly into your code, and that's called literal data. You're not making a variable, it's actually written directly into your code. Literals, values written directly into a program's code, not in variable storage. So there's a different way of doing that for each of these 4 basic types of data. For integers, you just write them down as normal math, right? You can write a 0, you can write a positive, you can write a negative, you could actually write like +5 with the plus symbol. That's optional, you don't have to do that. Not too surprising. With floating points, you have 2 options. You can either write them as decimals, right? I have an example there. 269.624, you can write that into your code, or you can write them as scientific notation using this E notation, right? Scientific notation has that exponent, the times 10 part. So you might actually see a floating point number written as 2.69624E2, which means 2.69624 times 10 to the power 2. Now, hopefully you realize that those two are actually the same number, right? 2.69624 times 10 to the second power actually is the same as this other number. So there's 2 ways of writing the exact same number. That would probably show up in your output if your floating point data gets very, very large, right? It'll probably come into output by default in this E notation, so you should be ready to recognize that and read it if you need to. Now, characters, right? Character data, if you write that as literal data, we use single quotes for that. So you might see single quote capital Q, or single quote digit 5, or single quote $. Those are individual characters. Now notice that's different from string literals where you use double quotes for that. And we've seen that all through our prior labs and exercises whenever we're doing output. Strings are double quotes. Single characters are single quotes. So kind of be careful about the difference there. And of course, for Booleans in your code, you would actually really write the word true or false to indicate a Boolean value. Hopefully that makes sense. Another thing here, escape sequences. So we're talking about characters, right? And we said it's mostly stuff you'll see on the keyboard, but there are some characters in ASCII that you actually can't normally see and you can't normally type on the keyboard. So escape sequences are a way of telling your C++ program that you want one of these symbols. Codes to represent certain special characters, and how you indicate them is you prefix them with a backslash. You write backslash first and then some kind of code to indicate the escape sequences. Here are some that are shown to you in the book, right? It's not all of them, but it's some important ones. So \n stands for a new line, and that's the same as the enter key. Okay, causes the cursor to go to the next line for subsequent printing. So you could put this in a double quote string literal, and that's a really short way of entering the enter key for a new line. Now, previously, we've been using the constant end line in our exercises in labs, right? ENDL in C++ indicates a new line, but this is actually a shorter way of doing it, and you can embed this within an existing string literal. So a lot of old school programmers will probably use the \n code more frequently because it takes up less space, but if you want to keep using end line instead, that's perfectly fine, right? The tab, right? The tab, jump a couple spaces over to the right in a piece of writing, not something you normally see. So in a string literal, you would write \t for a tab, technically a horizontal tab. Those are probably the ones right there that we will use the most often in our work in this class. \n for a new line, maybe \t for a tab. The rest are a little bit exotic. We might not actually use them, but it's interesting to know about them. \a for an alarm, actually, depending on the computer, should make an audible beep out of the computer, depending on how it's set up. \b would indicate a backspace. \r would indicate a return. Right? Again, these are all things that are invisible. They don't actually have visible glyphs to them. Now, If you want to actually see a backslash, that's a problem because backslash indicates I'm about to see an escape character, like new line or tab. So if you want to see a backslash in a string literal, you've got to say backslash backslash to say, here comes my escape sequence, and what I want to see is actually a backslash. So 2 backslashes actually come out as actually just 1, right? Backslash single quote sees a quote, and again, if you want to see a double quote in a printed string, that's a problem because normally the double quote would end the string. So if you actually want to see it, you use the escape sequence backslash double quote, and then it actually shows up in your output. So keep that in mind. These are all things that you would embed in a string literal or maybe a single character. So I think that's a pretty good overview of the fundamental types that exist in C++. And again, they are the same for any language that's coming out of the C branch. So this story is the same as C, this story is the same in Java, et cetera, et cetera. So you kind of know this for a whole bunch of languages all of a sudden. If you're in my class, the next time we're in person, we will probably do this lab 2.3, the rectangle area and perimeter lab. And you basically just write a whole program here. The goal here is to develop a program that computes the area and the perimeter, specifically of a rectangle with length 8 and width 3. And of course, I would ask my students to write a test script in advance so they know what the correct answers should be. This is still not a lab where we're using SYN to get user input from the keyboard. That is what we'll start doing in the next chapter, actually. But so far, we're still doing things that don't take user input. And then my students would write the source code for that. They might possibly look back to the last lab to kind of see what the structure is for the circle area program, which is honestly a little bit similar. But when we do this lab, we will be writing the whole program from scratch from start to finish. So hopefully that'll be a good exercise. Now, when we come back next time, we're going to look at the end of chapter 2, and we're going to look at issues of strings. Now, strings, they're not a basic data type. They're a compound data type built up from a bunch of characters. So that's probably the next thing that we should investigate more closely. Plus the idea of variable scope. When you declare a variable, where is it accessible in a program? And also more issues of styling to make sure that our programs are well written so other people can read them and help us with them when we need to. But that'll be next time. I'll see you then.